Swayam Prabha. Digital India. Educated India.
Welcome to this next lecture on vibrations of plates and shells. In the last class we started describing the Rayleigh Ritz method. So we will continue with that. So in the Rayleigh Ritz method, the mode shape of x is estimated as a weighted sum of some polynomials. Okay, some functions. Some functions, a set of functions. Okay. Now the kinetic energy max turns out to be omega square, okay, times psi m, the kinetic energy function. Okay. Then the potential energy turns out to be V max, okay, whatever it may be for the particular system. Okay. Then what do I have? I have omega square. So now psi m contains f of x and its derivatives, so that contains gj's, and these are integrated so that the space goes away, so it's largely a function of gj and the material constants. So it is with the V max. Okay. So I have omega square as Vm by psi m. Okay. And now what is the Rayleigh Ritz method? Rayleigh Ritz method. And these have satisfied the geometric conditions. Okay. So they are admissible. Admissible. That means each one of these phi j's is admissible. Okay. So the Rayleigh Ritz method now says that we are going to minimize this omega square m with respect to the gi's. Okay. So I set omega m square, the minimum is del gi equal to 0, I going from 1, 2, 3, etc. Okay. So you see that in trying to find the fundamental, as a bonus we get a bunch of equations that provide higher natural frequencies also. So how does it look like? Del omega square by del gi is equal to the numerator psi m del Vm by del gi minus Vm del psi m by del gi divided by psi m square. We simplify this, we get del omega square by del gi is equal to psi m del Vm by del gi by psi m squared minus Vm by psi m squared del psi m by del gi, that is equal to 0. So I get 1 over psi m del Vm by del gi Vm by 1 psi m is minus omega m squared, then 1 psi m, okay, and del psi m by del gi equal to 0. If we remove this psi m, I get, okay, let me write it as, let me not bring in this index, del Vm by del gi minus omega square del psi m by del gi equal to 0. Okay, this is the set of equations where I is the index, I goes from 1, 2 and so forth, and as many number of terms I have taken in my summation. Okay, so this results in a metric set of equations or a generalized eigenvalue problem. G, the vector minus omega square m, again G, the vector of coefficients is 0. So this is a generalized eigenvalue problem. Okay, if I multiply by m inverse, I get m inverse k minus omega square I into G equal to 0. So you can see that it looks like a minus lambda I into x. Okay, the eigenvalue problem. And Kij, the elements in this matrix, and this matrix, they can be straight away given. The I comma jth element in the matrix is given by del square Vm by del Gi del Gj, and M I comma j is given by del 2 psi m by del Gi del Gj. Okay, so let's work this. Let's take an example now. Let us take an example of a cantilever beam. Cantilever beam. So this is my cantilever beam. X equal to 0, x equal to L, okay, and the displacement in a mode shape under free conditions W x comma t is the mode shape into the natural frequency some omega t plus phi. So what is f of x? We choose, because as an example I will choose a small number of terms. So g1 x over L whole squared plus g2 x over L whole cube. Okay, so what is the cantilever boundary condition? F at 0 must be 0, f dash at 0 must be 0, okay, which this satisfies. Okay, so this is an admissible function. So these are my phi i's. Okay, So now what is V max? V max is integral 0 to L E I by 2, okay. Let us straight away write it. Let us straight away write it. D, yeah, without f double dash of x whole square dx. Okay, so it comes from del to w del x square. Okay, so then what is psi m? The kinetic energy function, that is integral 0 to L 1/2 of m, then f of x whole squared dx. Okay, it's part of m omega square w. Okay, in half m omega squared. Okay, it is part of that. So therefore omega square goes away and you end up with the function. Okay, because w is f of x, w dot is omega times f of x. Okay, so now if we substitute my f of x into this Vm and psi m, I get Vm and do the integrations. Okay, Ei by L cube 2g1 squared plus 6g1 g2 plus 6g2 squared, and psi m becomes m L by 2 1/5 g1 squared plus 2/6 g1 g2 plus 1/7 g2 squared. Okay, so now we have to do del Vm by del Gi. So we'll do d1. Okay, so that becomes 4 Ei by L cube into g1 plus 6 Ei by L cube into g2, then del Vm by del g2 comes equal to 6 Ei by L cube g1 plus 12 Ei by L cube g2. Okay, and what about psi m? We get del psi m by del g1 is equal to ml by 5 g1 plus ml by 6 g2, and del psi m by del g2 sorry is equal to ml by 6 g1 plus ml by 7 g2. Okay, so if we write these equations, what do we get? We get, first equation is del Vm by del g1 minus omega square del psi m by del g1, that is one equation, is 0, The second equation is del, so this is one equation. Second equation is with the second coefficient. So there will be as many equations as the number of coefficients. Del G2, that is equal to 0. This is the second equation. So if we assemble this, okay, if we assemble this, I get K G minus omega square M G, G as in G1 G2 vector is 0. Okay, and what is K here? K in this case is 4 EI by L cube, 6 EI by L cube, 6 EI by L cube, 12 EI by L cube. That's K matrix. And what is M matrix? What is M? M is equal to ML by 5, ML by 6, ML by 6, ML by 7. Okay. So there is a shortcut. There is a shortcut for arriving at these matrices. There is a shortcut. What is the shortcut? Shortcut is this. K12, for example, Kij. Okay, Ij. In this case, we will take a look at K12, K1 comma 2 is given by del Vm by del G1 del G2. Okay, that means what? Del 2 G1 G2 of integral 0 to L EI by 2 f double dash of x whole squared dx. So that is equal to integral 0 to L del 2 del G1 del G2 EI by 2 f double dash of x squared dx, or integral 0 to L del 2 by del of G1 G2 EI by 2 G1 x over L whole squared plus G2 x by L whole cube double dash whole squared dx. Okay, so let's continue. Integral 0 to L del 2 by del G1 del G2 EI by 2 into G1 2x by L square plus G2 2, no x here, it's a double dash, so 2. Okay, and that gives me 6x, okay, 6x over L whole squared dx. Okay, so this ends up as integral 0 to L del 2 by del G1 del G2 EI by 2 4 G1 square by L fourth plus 24 G1 G2 x by L cube. Okay, not L, something got missed. This is L cube, so this is L5. Okay, so in the double dash L will come out the same. Okay, this is L5 plus G2 square 36x square by L to the power 6 dx. Now if we integrate, what do we get? We get integral 0 to L. We do the differentiation now, so I get EI by 2. Once with G1 this survives, next with G2 it won't survive. Once with G2 it survives, then with G1 it won't survive. Okay, so you get EI by 2, only this survives, which gives me 24x over L5, or rather 12x over L5, which is dx, which after integration is EI 12 x square by 2 L5 over 0 to L. Okay, so which gives me 6 EI by L cube, which is K12. So if you remember, K12 was this. Similarly K21. Okay, so that's how. So just this derivative gives you the K12 term. That was the whole idea. Okay. Similarly, Mij is given by del 2 by del G1 del G2 of psi m. Okay, that need not be shown again. Now, having calculated, okay, with two terms and higher order terms, okay, I will give you a table for the estimated natural frequencies of a cantilever beam. Okay. On some other day I will show you the mode shapes. Okay, but today let me just list the natural frequency. So the table is this: number of terms chosen, okay, then mode 1, mode 2, mode 3, mode 4. So if you have just one term, then you can estimate the first natural frequency. Okay, now what is this value? This value was, if you remember, lambda fourth was given by rho dash or m dash, I don't remember, rho dash, maybe rho dash omega square by EI, or m dash omega square. Let me keep it as m dash, mass per unit length, m dash omega square by EI. What is lambda fourth? Okay, and therefore lambda is the fourth root of this thing, fourth root of m dash omega square by EI. Okay, and we are looking at lambda times L value. Okay, we are looking at lambda times L value. So if you remember, for the cantilever beam, the characteristic equation ended up as some cos hyperbolic lambda L into cos lambda L, I think, was equal to plus or minus 1. Okay, and that if you solve, you will start getting lambda L values. That is the lambda L we are talking about here. Okay, so this is lambda L values. Okay, straight away, not the natural frequency. So then the 2 is, if you take two terms, then you get 1.88. It's a better estimate, and you get one estimate of the second. If you use three terms, you get 1.875, which is almost there. Then you get an estimate of the next two, 4.715 and 10.869. If you use four terms, you have actually already converged by 3, 4.707, 7.959, and the fourth mode 16.781. And the exact values are exact, quote unquote exact values are 1.875, 4.694, 7.855 and 10.996. Okay, so you can run this in MATLAB and check for yourself. Okay, in maybe in the coming classes I will show you MATLAB calculations and show you the mode shapes. Okay, we are run out of time almost, so I'll close the lecture here. We'll continue with this topic in the next class. Thank you.